Good morning, everyone. My name is Eduardo Caro. I'm going to be the chairman of this session. This session is gas and electricity demand, okay? Today, we have 3 talks. The first talk will be presented by Eugenie Genov from the Brussels University. Eugenie, can you hear us? I invoke you.
Yeah, I can hear you.
Perfect. Eugenie is not here presentially, just virtually, and he's going to present his presentation, and afterwards we have a couple of minutes to ask questions. Okay, let's start. Enjoy.
Hello, everyone. My name is Evgeny Genov. I'm a PhD student in Free University Brussels in Belgium. Unfortunately, I couldn't make it today to Oxford as I'm still waiting for my visa. So I'll be presenting this talk online, pre-recorded, and I'll be there also to answer your questions after this. I'd like to talk about my research on building models to generate synthetic load profiles of buildings from metadata. And what I mean by that is often in the project that we are working on, we have already a bulk of smart meter data that is available, yet at the same time there is also often buildings that don't have such luxury, and then there is no high granularity data. They would have they wouldn't have the smart meter. They would have like a analog meter in place, and so there would be no historical record of electric consumption in these buildings. So the objective here is to create the profiles for the buildings that are out of sample, and we could train the model on the buildings that have such data available. For training and verifying the model, we use the Irish Smart Metering Project dataset, particularly the control group, which consists of 929 residential buildings. And besides the records on the consumption or the smart meter data, there is also metadata available from the surveys that were filled in by the participants in the experiment, and these are the features on the characteristic of the building. For example, like the floor area, number of residents, the type of the house, the status of the ownership, whether it's rented or it's owned directly by the resident, the year of construction. There is also features on the whether particular appliances for the cooking or heating are used. And since the data set is also anonymized, so the weather that can be used as an external feature is averaged over 3 major cities in Ireland, and the features that are listed in the slide are used. For splitting the data, to verify such approach, we need to generate the profiles and then match against the real profiles and test for the accuracy of the prediction. And so the part of the part of the subset of the buildings is reserved for test. So the model is trained in sample, and then the model is tested on the out of sample buildings within the same period and also in the future period. So how does this work? In order to generate synthetic load profiles for buildings, we need to train a regression model that is trained globally across entire dataset, so that the model extracts a global set of parameters that infers patterns that can be transferred to the buildings out of sample. For the global model to work, each of the time series need to be normalized to the same scale, and for normalization I use division by the yearly consumption. This already the scale that is used typically for building and using standard low profiles, and also to remove non-stationarities we apply log transformation, and we also extract the calendar features as the predictor variables for the model. For the implementation, the gradient boosting model is used, but the LightGBM implementation, and after the predictions are made, it's denormalized back to the original scale, and also the same goes for the log transformation. Here's how it looks in practice. The static load profiles are generated for the selected date range and also for the selected characteristics of the building. There's continuous variables like year of construction and yearly consumption, and also the categories, whether the residents are employed, retired or unemployed. And here, for example, there's a detached house that is rather old, and if we change that to an apartment that has like a much more recent construction, then the overall consumption over the selected period drops significantly. That's normally that the more modern buildings that are built to be more energy efficient. So if we look at the test results when validated against actual profiles within the out of sample subset of buildings, then we can see that the static low profile generator gets much better accuracy compared to the standard low profile, which is the usual practice in such applications for using the data for buildings without smart meter data. And the first benchmark method is the standard low profile that is commissioned by the energy regulator in Ireland, and that's normally derived from the historical smart meter data. And the second benchmark is the mean normalized profile of the training data. What is also interesting that when using all features, the accuracy is slightly worse. There's a bigger error than when using a reduced set of features, and that can be confirmed when we look at the feature importance bar plot. The most important features would be the categorical features, and then also the age of the house and the floor area. So the features that are in the blue bracket, these are the features that produce better accuracy. There's no clear-cut reason why the model that uses full set of features shows a bigger error than the model with a reduced set of features. We suppose that has to do that some of the features would be already correlated between each other, and that would produce additional noise. And it's also possible that some of the features that are result of the survey would have more inaccuracies and missing values in the data set. Then what is also possible is to use weather as a predictor. As I mentioned earlier, the features like the temperature, the speed of the wind speed, and the surface pressure. So these features are added as the external features, and then they bring the error further down across all metrics. We can also generate static load profiles and use them as forecast, particularly for the buildings that don't have historical data. So here is the results for the accuracy, for the performance of the model, for the test subset that is in the future compared to the in-sample training data, and then the results are consistent with the accuracy that are shown before. So the synthetic load profiles show consistently lower error than the standard load profiles that are typically used. And what is also interesting for the case for the newly connected smart meters that might not have enough data for training the local model, but the recent measurements can still be used for improving the accuracy of the forecast. We test the variation when we can use the lagged features, particularly the lag consumption from the same day before and the lag consumption from the same hour the week before. So two additional variables, and this has the lower error as well. What is interesting is when using this approach of training a model, like a regression model, to generate synthetic profiles, we come across the duality of the problem that if we use the objective of minimizing error in every point, and then the model is trained with the objective of minimizing the error, then typically as like a data-driven forecast, we can see that the final prediction would be rather conservative, and then the profiles that are generated, they would have overall lower peak values than the real profiles, but yet at the same time they would have the best accuracy when validated against the real data. So then the question arises whether we can generate the profiles that are realistic in a way that they will be more similar to the known profiles in terms of distribution of values, and they will be more similar to a human expert that views these profiles. We can also see this discrepancy in the distribution of the values. So for the synthetic load profile, there is more values in the middle, while for the real consumption there is more consumption in the tail and in the next to origin of the distribution. This mismatch is also reflected in the aggregated yearly consumption. So for the synthetic load profiles, the yearly consumption when aggregating all values over the year would typically underscore the actual yearly consumption. As the next step, we generate synthetic load profiles that imitate the actual consumption data in terms of distribution of values and in terms of presence of the peak values of the right magnitude, not the overall consumption, not the overall accuracy of the prediction. In order to do this, we can model the error, the additional error to the existing forecast. To model the error, we assume the distribution of the error. Here is the example for a log normal distribution, and we can see then when the error is modeled separately on top of the produced forecast, then the distribution, the original synthetic profile distribution that is in orange is more distributed over the value and the tail regions of the real consumption. So it looks it would be more similar, and the peak values would be more there's more peak values that similar to the real data. And to generate to estimate the parameters for the log normal distribution, we can use the estimates for the point load predictions that are already generated by the model, and the confidence intervals that are already generated by the model. Here is the example after modeling the error separately. We see that the daily load profile, the 90% quantile has increased further up, although it still doesn't replicate the aggregate mean profile for the actual data. And here's the difference when after modeling the error using the log normal distribution for the aggregating yearly consumption, that we can see that the yearly consumption for the produced profile is the distribution is more centered around 0. However, the outliers became more prominent and more critical, with the percentage error going up to 50 and 90%. So it's worth looking more into other distributions and how to address this particular issue. To sum up, the proposed gradient boosting machine globally trained model enables generating customized static profiles for the buildings where there is no smart meter data available. Then the output of such model can be probabilistic, so it would reflect the confidence interval at each point, which is useful at identifying regions for the peak values. Weather and lag features can also be used as external predictors, and they improve the overall accuracy of the model. As a data-driven model with the objective function to minimize the error, the results tend to be rather conservative and underestimate the peak values and the top quantile values. And in order to address that, we try to simulate error separately, and this can be done using the existing estimations for the uncertainty intervals. Thank you very much, and I'm looking forward to your questions.
Okay, any question?
Okay.
Yes. Eugene, are you there?
Yeah, I'm here.
Okay, you can connect your camera if you prefer.
Yeah, I'm trying. I don't know if it's working. I think so. I can see myself.
Okay. Okay, then any questions? No questions? Oh, okay, then thank you very much, Eugene.
Okay, that's good. Hope it's clear. Thank you very much.
Our next presenter is Colin King from the Marquette University, United States. By the way, the previous presentation and these presentations are presented by students, and therefore they are submitted to the competition. You can use the HOPA application in order to rate those presentations. Thank you very much.
All right. Hope you're able to hear me online. Hello, everyone. Welcome to my presentation. Today, I'll be discussing some of my research titled Multi-Source Iterative Load Shifting Disaggregation Algorithm. I have to give thanks to the gentleman who presented before me. He actually covered a lot of the topics that I'll be introducing, so it'll give me a little more time to get into the details. 18 minutes, 17 minutes to get through the entire algorithm is a lot, but of course, I'd be willing to answer questions, and we have a coffee break after this, so please approach me if we don't have enough time to answer all questions in this presentation. Special thanks to Richard Povinelli. He is my doctoral thesis advisor, and he works on this research with me. To begin, just a little bit about myself. On the left there, I'm pointing out I'm a doctoral student at Marquette University, Milwaukee, Wisconsin. Wisconsin, the blue state. Also in Wisconsin is a company called Marquette Energy Analytics. They're sponsoring this work. They produce hourly, daily, monthly, and out to a few years forecasts for the distribution companies spanning the United States. The roadmap for the presentation today is going to start off with a brief introduction, starting from square one of natural gas consumption. What do we use it for, and what my problem statement is. Then we get into the generalized topic of temporal disaggregation, how I'm applying it to my problem, and which is the algorithm is titled the multi-source iterative load shifting disaggregation algorithm. And then finally, I will very quickly go into some results. Again, very specific to the application, but I'm trying to present it more in a general sense so others can get some ideas on how it might be helpful to apply in their research. So tying some relevancy into today's talk, my talk, natural gas, fossil fuel energy source extracted from the earth for many uses spanning the residential, commercial, and industrial markets. Primary use across the world is for space heating. The relevancy, which I'm tying in, is here we are in beautiful Oxford, UK. They use quite a bit of their space heating fuel, which is of natural gas. They are currently ranked 11th in the world for how much gas they consume. It's about 2.1% of the total gas consumed throughout the world on a yearly basis. The US is ranked number 1. The company that I'm working for, I'm very proud. We are starting to move a little bit more towards alternative sources of forecasting, alternative sources of fuel, such as electricity and eventually some non-renewables. Below in this black box, I have a specific date, which is January 14th, 1962. And I have this picture, which I actually took on a walking tour in Oxford 2 days ago. This is the Radcliffe Observatory. I think it's actually also called the Radcliffe Camera. And at this location on that date in 1962, a late Dr. Ebsen was having an experiment because it was the coldest temperature recorded to date in Oxford. And I thought it was funny. I was reading some of his notes. He was explaining all the experiments he was doing. And the note I found most entertaining was that his wine keg had froze during the study. So even though Dr. Ebsen was having a good time that day, he was cold, but he was staying warm inside. We have to ask the question, what would have happened if there was no heating source on that very cold day? We call these days extreme cold weather events, and these are the days where natural gas forecasting becomes the most important. And so gas distribution companies, which I'll commonly refer to as local distribution companies, so local meaning we have to provide gas from the immediate area into Oxford, they need to know how much gas to provide or have on standby to adequately service their customers, whether it's a warm day like we have today or an extreme cold event like they saw in 1962. It's more of a responsibility because if they do have an issue where gas runs out, it becomes a very serious problem. Imagine trying to live in one of these extreme cold events. I'm not going to get that dramatic in this presentation, but it is a relevant topic of really just being responsible with this fossil fuel energy source and making sure that we can adequately service all customers. I'm going to start moving into the general overview of temporal disaggregation. This is not a new topic. There's some wonderful work published throughout a number of journals, but where I'll be starting is just simply with 2 time series. Here we're given time series Y, capital Y, and that is representing a low frequency series, and that is a non-uniformly spaced series with relatively long time steps. In my application, that would be about monthly, anywhere from 20 to 40 days. Low frequency can be anything that apply to your problem. Could be hours, could be minutes, but in this application, it's going to be monthly observations. In a forecaster, one of us requires a lowercase y time series, which is measured at a higher frequency. In this case, it's daily. We do not have lowercase y, so we need to use temporal disaggregation to obtain it. Here I have the representation of our low frequency series, capital Y, and uppercase capital Y is our low frequency series, lowercase y as our high frequency series. And you can just see the first observation of Y1 spans from day 1 to 30, while the high frequency series has daily observations. They measure the same quantities, but are measured at over different intervals. I have the intervals pointed out here because as I get more in my application, there's a lot of time series, a lot of things to keep track of. The general idea is, though, that we have observations spanning a specific set of time. Our high frequency series needs to be disaggregated into the underlying days of those intervals. I'm going to bump the bottom image up to the top. Start with the inverse of the problem. If I had actually a daily time series, we know that if we aggregate the days within a month, we would obtain our uppercase Y. And I'm denoting this operation of summation the underlying days as script A. The inverse of this problem, A inverse, is the disaggregation operator, and that's what we're going to be diving into today. My approach to how we are disaggregating these time series, which takes the low frequency series and the time intervals and disaggregates into a high frequency series. As I mentioned, temporal disaggregation isn't a new topic, but primarily used to generate more high frequency data that we can use to estimate parameters. The next extension of my work would be using the daily time series to train a model and forecasting at shorter intervals than months, which is very helpful to the local distribution companies as they need to know day to day, week to week, could be even shorter or longer than that. Anything shorter than monthly observations is helpful for them. I'm going to be mentioning this flow reconciliation constraint. If you're familiar with the hierarchical forecasting, I have a really simplified version of this flow reconciliation constraint here. All that means is that we need to use the known information that we have available, and we need to make sure that is preserved as we do our disaggregation. That means that the underlying days should sum to the original monthly values. That kind of bounds our solution space and is a pretty primary part of this algorithm. To introduce my application, before I just seen one time series, capital Y. In my application, we're considering time series almost as pipelines. Here we have the town of Oxford, multiple operating areas. We don't have to worry about that quite yet, but to service the thousands of people living here, we have multiple pipelines flowing into the service area. I've named them as pipelines or time series A, B, and C. These time series have overlapping intervals. They're non-uniform, so they could be anywhere from 20 to 40 days. And the person sitting in the control room, making sure that gas is correctly flowing through the system, needs to know on a daily basis how much gas is consumed. So a little bit, just more time series we have to keep track of. These time series with their overlapping intervals produces some problems, and that is what we're trying to introduce in the multi-source part of the algorithm title. If I were to extract time series A, which I'm having here as an actual pipeline, looks very similar to what we had in time series Y. Instead of the actual intervals of script T, I have a lowercase a, and that's just going to be indicating how many days are in each interval. So if I look at observation A1, we can see that there's 4 days in that interval, and it has a measure of 48 units. I understand here in Europe, most of the time, natural gas is measured in kilojoules. I'm familiar with decatherms. So pardon me if I reference decatherms, my results are in decatherms. But over days 1 through 4, we know that time series A, 48 units flowed through the pipe. So to introduce really the novel aspects of my algorithm, I already mentioned, we have ways to temporally disaggregate time series, but when we have a dynamic system like this with multiple pipelines flowing in at the same time, we want to use all information, all relevant information available so that we can obtain an accurate representation of the daily flow. So that's where the multi-source comes into play. We are generating this daily time series in a two-step process. Very familiar with this process. The general outline is a prediction phase. We're using multiple linear regression to generate a flow profile. So thanks to the gentleman who presented in front of me, he kind of got over what a profile is. And then the second phase is the update phase, where we're using a linear piecewise update phase, where we're shifting or redistributing the flow of the low frequency series into the underlying days. And that is where the shifting part of this title comes into play. So from here on out, I'm just going to go through the steps of my algorithm. We have 5 total. It is an iterative algorithm. The steps, I don't know if you're able to read that text very well with all the beautiful natural light in this room, but steps 4 and 5, those are the iterative aspect of this algorithm. I'm going to spend a little bit more time on that. But really, step 1 of any project, we are collecting our inputs to the algorithm. Here, I'm going to be using 3 time series, as I showed in the image. And then I'm also going to be using S independent correlated variables with natural gas consumption. There is a direct correlation between temperature and consumption, which then relates to demand, which we will be eventually forecasting, not a part of this presentation. But here you can kind of see the nonlinear relationship that we have with just temperature and consumption. The output is a single time series, even though 3 time series are going in, and that is the daily consumption over the same time domain of A, B, and C. So that's step 1. Step 2, we have 3 time series with their overlapping intervals, A, B, and C. We want to get them on the same time domain. Often used as a benchmarking method is naive disaggregation. We are going to be using naive disaggregation to turn time series A, B, and C into time series A bar, B bar, and C bar. Very simple idea where if we do have 48 units measured in time series A, and we know that there's 4 days in that interval span, we just divide 48 by 4 and assign each of the 4 days the same value of 12. We do that with each of the time series A, B, and C. They're spanning now the same time domain. Once we have the 3 time series over the same time domain, we just simply aggregate them on day D to produce our first, this is really technically a profile. It's not a very good profile, but Y hat indexed by day D, and it's just a summation of A, B, and C. If we wanted to look at the 3 time series, I guess 4 time series now graphically, this lower line is too small probably to read in the back. Lower line is time series A, naively disaggregated, so we get that block-like structure. B is in the light blue, and then C is in the darker blue. We aggregate them all together, and we get this top blocky line. That's just Y hat at this current iteration, really before any iterations have occurred. So we're going to set everything aside in our back pocket, time series A, B, and C, as well as time series A bar, B bar, and C bar, and the underlying days in each interval. There's a lot to keep track of in this algorithm. Setting that on the back burner for now. We're not going to prepare our exogenous variables. Those are really just the independent correlated variables. For this presentation, I'm only using 2, temperature and wind. As you saw on the plot before a few slides ago, there was a non-linear relationship. We're applying some transformations here to obtain heating degree days, wind adjustment, and cooling degree days. I'm not going to go over those too much right now, but I've seen several presentations already mentioning this type of transformation, and really we just want linear representations of these variables. We plug all of those variables into design matrix X with our bias vector of 1s. That's the load that is not affected by temperature. That's everything from drying your clothes and all the other uses for natural gas that is not used for space heating. And now we enter the first iteration of our iterative steps, steps 4 and 5. Steps 4, very simple, multilinear regression. We have our design matrix X and our naively aggregated version, Y hat. We're solving that system. And really the problem of temporal disaggregation, or I should say the mathematical problem, is that it's ill-posed. It's an over-constrained system. So we obtain a set of weights right away from this relationship, solving that equation right there. We're going to turn around right away and use that the new coefficients we just generated using sum of square error to produce Y tilde. The idea of this is to introduce variability into our flow profile that is lacking from the naive disaggregation. That is the dashed gray line, which you can see a little bit more variability. Some methods would, if we were talking about generalized least squares, this is very similar to what we've done so far. We call it a day, we say the dashed gray line is our answer, that is the daily consumption. Because we know, or I guess we're working within the overconstrained properties of temporal disaggregation, we're approaching this as a little bit of a constrained optimization problem, not in the true sense, but we want to take small steps towards a solution, evaluate the error. Based on the error in that update phase, we're going to be redistributing the flow amongst the underlying days. So that really comes into play in step 5, where we are distributing the flow based on error. This is the part that's a little tricky to explain in a short presentation. I'm going to do my best, and again, hopefully have a little bit more time for questions at the end. But I'm going to start with this first observation I've mentioned, A1, which has 48 units measured over 4 days. We know that this time series A contributes 48 units over the first 4 days. What we do is we're going to be subtracting the naive, which is A bar, which is solid straight 12 units on the first 4 days, subtracting that from our Y hat. If we think what that actually represents, that's the contributions of time series B and C, if we're subtracting A out of our Y hat. We then subtract our Y hat from our Y bar to get an estimate of what the actual interval was for just time series A over those 4 days. I'm going to bump up really the red square on this next slide to give a little bit more closer view. If we look at the gold line, again, that's just 12 over the first 4 days. That's from the naive disaggregation. If we are to subtract the error off of our Y hat and our Y tilde that was developed in step 4, we obtain this error, which is in the light gray dashed line. So we have an estimate for our first interval, except we want to use the most, thank you. Oh, we want to use the most relevant information, meaning we know that there's only 48 units in this observation. If we took the integral underneath the gray line, it would be exceeding 48. So through that piecewise update phase, we constrain the flow so that it equals 48. And then based on that small step optimization kind of approach, we take a small portion of that constrained version, and that's what we have here in this red line. Do this many times, traditional optimization problem. It looks very nice in this problem because I made up the data to help me explain it, but eventually we start to see more and more variability introduced in this first observation. This first observation of A1 is then brought back into our original flow profile. And over each iteration, we're able to kind of recreate the variability that you would see in a true daily series. For the case study, I've kept it relatively simple. There's a lot of other metrics such as preservation of movement. But to put it in layman's terms, I have RMSE and MAPE, the unit list. And as we can see, we're kind of comparing it to that benchmark model of naive, generalized least squares, which is kind of the first few steps of this project, and then ARIMA. And we can see that there is, for this specific application, an increase in our performance for the iterative load shifting disaggregation algorithm. So I think I did not leave enough time for questions, but at this time, I'd love to answer any questions that come up. Again, I think we have a coffee break after this, so please feel free to come see me. I also changed the name of my presentation. It does not match what's on the Whova app, but just in case there's any confusion, it's called the iterative load shifting disaggregation on the Whova app. And again, I am a student, so if you have the time, please feel free to rate me. I said I was a student, didn't say I was shameless, so yeah. Yeah, and thank you, everyone.
I do have a question, but it's not real quick. So you plotted MAPE and RMSE as parametrics. How did you actually have actuals to compare it to? How did you actually calculate errors?
Yep. So well, we don't have Y. That's the whole problem. In the research part of this, we had smart meter data. The problem that we kind of started to discuss, you and me, but the problem with smart meter data and natural gas is very new metering systems, very expensive to get into place. They tick only on the decatherm. So even though they are taking much higher frequency measurements over the month, maybe 3 to 5 days, If we have a tick on the third day, really that gas is burned over day 1, 2, and 3. So direct comparison to a true daily series, a little more difficult. For the sake of the paper that I'm writing, we do have a true daily series, and that is published. Well, will be published, hopefully. Thank you again.
One of the issues is, if I understand correctly, we keep that constraint of the adding up to the weekly value the whole way through. But as we kind of go through the week, the opportunity to potentially update that constraint, presumably also have better knowledge about what the might be.
So that's what this algorithm is kind of taking into account. As I showed with the 3 time series, those 3 pipelines, the pipelines can be various sizes. One could be drawing out of storage. One could be drawing from a tube from France. One could be huge. So the reason that we're looking at the individual measurements of A, B, and C is that if A did meet its constraint that it added up to 48, but we know there was an extreme cold event on that day, C might also be very high. And because 48, we're limited to that, and time series, let's say B expands from day one to day 7, we're taking into account that on day 4, we need to shift more flow from the time series B into that time, that interval. So that's the part that I tried to avoid explaining because I knew I wouldn't have enough time, but I'd be happy to sit down with you and get more into it.
Thank you very much.
Thank you.
Okay. Good morning, everyone. The next presenter, it's me. I am Eduardo Caro from the Technical University of Madrid, Spain, and I'm going to talk about how did we model the COVID lockdown in Spain concerning the electricity demand forecasting. Well, as you know, one of the main peculiarities of electric energy is that it cannot be stored. Therefore, there must be a perfect equilibrium between demand and generation at all times. Here you have a photograph of the Spanish headquarters of the Spanish transmission system operator called Red Eléctrica de España, and they really require an accurate forecast. I'm proud to say that we have programmed the actual software that predicts the electricity demand in a real time. In fact, here you have the yellow line is the actual demand, the real-time demand, and the green line is our forecasted demand. We made forecast from 1 day ahead to 10 days ahead, and our accuracy is around 1.5%. The model is based in 24 independent seasonal ARIMA with regressors, and we have a second step which unifies these 24 independent models with an ARMA models. You can find more details about the mathematical model in this reference. Well, let's talk a little bit about the variables. The most important variable is the temperature's influence. Here you have the relationship between demand and temperature for working days, blue dots, Saturdays and Sundays, green and red dots. As you can see, here we have a significant nonlinear effect, and this effect also depends on the hour of the day. We have modeled those effects using spline regression models. We have up to 2,000 parameters to be estimated because we have not only considered the maximum daily temperature, but also the minimum daily temperature. We have also considered the interaction between working days and weekends. And we have also considered the temperatures of the previous days. In such a way, once that we have estimated those parameters, we can quantify the effect for every temperature, for every hour of the day, depending on the maximum and minimum temperature. Concerning the holidays influence, in Spain, the working calendar of Spain has 8 national holidays and plenty of regional holidays. Each national holiday has an effect over the demand which depends not only on the hour of the day, it depends also on the time of the day of the week, and it also affects the previous and following days. We have included in the model a set of binary variables in order to model its particular national holidays. With this, we have around 5,000 parameters to be estimated. Once that we have estimated those parameters, we have plots like this one. In this plot, we can see the effect of the national holiday, the 6th of January, over the domain, depending on the hour of the day, depending on the day of the week, and depending on the previous and the following days. Okay. Therefore, we can quantify the descent, the decrement of the demand for its national holidays, the 8 national holidays in Spain. Okay, and finally, considering radiation, we receive every day files from the European Center of Forecasting. For each file, we have a spatial resolution of 9 kilometers. And in each file, we have this data. By 3 hours time resolution and 9 kilometers spatial resolution, we have the 3 days in advance temperatures, 3 days in advance solar radiation, cloudiness, and wind speed and direction. We have included the information of radiation in our models, and we have decreased the average root mean square errors in a significant term, usually in the sunny hours. And finally, let us talk about COVID lockdown in Spain. In this plot, here you have the daily demand for the last few years. As you can see, we have a similar behavior in the previous years, pre-COVID years, and in the 2020, we observe here a decrement of the demand. How do we model this with this effect? By the way, this study has been performed after the lockdown. I mean, this study has been performed in 2021, okay, after the lockdown. In this plot, you have the working days demand for the previous days, blue, red, and orange points, and the demand of 2020, which is the time that we are about to model. Okay. How did we model this? Well, we have observed 2 parts, 2 stages: the decrement and increment of the demand. And as you may know, all the behavior of the demand depends on political decisions. We have a first stage of political decisions about confinement, hard confinement, light confinement, and we have a second stage about normalization, back to normality. Okay, we have modeled this using a linear shape in the containment phase and a quadratic model for the de-escalation phase. We have included the term of we have included the term not only for working days, but also for weekends. Caution, as you know, to make accurate forecast, it's really important to abbreviate modeling the past in order to predict the future, no matter if we are going to be confined or not. And then, well, this is the mathematical model. And a second effect that we have observed since the COVID is that the effect of national holidays is not as high as before. Here you have in the blue line the real demand, and in the red line our forecast. Our forecast was always lower than the actual demand. Why? Because of telework, telecommuting. I mean, the habits of Spanish citizens has changed after the COVID. In fact, we have studied, for example, this is just a national holiday in Spain. Usually, if this national holiday was from Monday to Friday, working days, the decrement of the demand is around 80%, 75%. In COVID, this descent is not so high. And this is happening for all the national holidays in Spain. Then we have modified the parameters in order to include this second effect, which is the effect of COVID on national holidays. And these are the results. I am plotting here the residual standard error of the 24 independent models. Okay, the blue line is the baseline model without any modeling.
the red line is the modified model, including the confinement and the escalation regressors, just 8 regressors more. As you can see, we observe a significant decrement of the variability of the models, of the residuals. And finally, just tuning the holiday effect multiplied by the decrement from 80% to 60%, we have decreased the residual standard errors. Okay. For confidentiality reasons, I cannot plot here more information about the forecasting errors during those years. Sorry. And that's all. We have been analyzing the COVID effect of the lockdown over the Spanish demand. We have proposed a model, and we are running this model, and which improves the forecasting accuracy. And that's all. Thank you very much. Thank you. Thank you very much. If you have any questions, yes.
Thank you for your presentation. It's really interesting. And I think the situation with COVID has created interesting problems. Other problems. In your opinion, this was a post-hoc analysis, from what I understood.
That's it. Yes.
In your opinion, what would you propose to an operator on how to make the models a priori adaptive to such, let's say, extreme distribution shifts? So how would you deal with the COVID-like situation in the future? But before you know that it will actually occur, what would be your proposal?
Well, interesting question indeed. But in our study, I mean, in our day-to-day basis, we just made forecast for 1 day ahead or 10 days ahead. Therefore, in our models, I mean, it does not make medium-term forecast, and therefore this point is out of our study. I mean, from 1 day to the next day, there is no change at all, no significant change at all. Yes. Yes.
So, question of going forward, since you are actually.
So Richard Povinelli from Marquette University. What are you doing for modeling, let's say for 2023? How are you building your models? Are you including the COVID, or are you going back to 2019, 2018, 2017? What things are you taking into account, you know, now with telework seeming to become more prevalent?
Okay, very good question. Every year we re-estimate the model. And before estimating the model, we analyze the errors during the previous year. If we have observed that the Spanish citizens' behavior on national holidays has returned to normality, we remove those. I mean, we tune up those parameters in order to put as the previous pre-COVID values. Okay, but we do year by year. At the end of the year, we re-estimate the models. Okay, thank you. Another question? Yes. Okay, that's it. Thank you.
I have similar questions. So you mentioned that it's day-to-day forecasting. You
Yes.
mentioned that there was a linear relationship first and then a quadratic relationship. So at the time when this happened, how would somebody have known that they should assume a linear or quadratic?
We didn't know at all. I mean, yes, during the confinement and all these weeks, I mean, we didn't intervene in the model. We didn't know. Any other question? No?
Yeah, you said you have a few thousand parameters, right?
Yes, that's it.
Don't you use regularization or something to decrease the number?
Well, in fact, we have thousands of parameters, but in global, we have to divide it by 24 because we have 24.
Still, it's a lot.
Yes, it's still a lot, but it's below 1,000 parameters. Most of the parameters are 0, 1 variables that it takes into account just 2 or 3 times. I mean, it's almost an empty vector with just 1 or 2 ones. For example, in order to model the 1st of May, we have a column of zeros and just ones just in the 1st of May. Therefore, we did not experience any divergence or any problem issues about the
And you said you had a 1.5% May, right?
Yes, for 1 day ahead.
Forge horizon, because you said you have forecasting a few hours ahead up to a week ahead.
Yes,
So
very
what
good.
do we find for?
yes. We made forecast at 10 a.m. in the morning for the 24 hours for the next day. Therefore, we have 14 values in one day ahead and 10 values for two steps ahead.
Okay.
Therefore, we have
So we find is the average of those.
exactly. That's it. Yes, that's it. Yes.
Say it again, it's the average of overdose. So
Sorry?
to make the 1.5% is the average.
Yes, of these 24 values for the next day. That's it. Yes. Any other question? No. Okay. Thank you very much. Thank you.